Alright, for this one, I'm going to continue the bone ESP. So to differentiate between enemies, since we had some issues with that last time, we're going to be using the runtime type info. So if you've ever wondered how reclass somehow knows your class info without having access to debug symbols or the .pdb file, it's actually pulling from a built-in type info in Microsoft Visual Studio's compiler. Obviously, it's not the debug info because a closed source game like L4D2 doesn't come with that. So instead, RTI is embedded class metadata right in the binary, and then we can just parse that manually like reclass is doing to get the object's class name and where it's derived from, and then use that to differentiate between the entities. I also want to build a little tool to manually map those indices between bones, so it's not as tedious to construct them. Let's say we wanted to find the smoker's runtime type info manually instead of relying on reclass. What you would do is you would take the v table to put this somewhere else. Let's put this in here. We're going to subtract 4 from it because we want the address right before it. And we're going to take this pointer that points to a structure. This structure is called the RTTI complete object locator, which is going to store a couple things, which I'll go over later when we start writing the code. But the one we really care about right now is the one on the C offset or the 12th offset, which points to the runtime type info. So we'll take this pointer, go to it, and the first member of this new structure, which is the type info structure, is going to be the v table to the type info. The second one is pretty much blank always because it's reserved, so it's always 0. And then on the third and so on is going to be the name of that actual class. Now you might have noticed that the class is or has some weird ass characters that reclass doesn't really have here. This is because reclass demangles it for us, so we're gonna have to do that manually. Class names are mangled by the compiler, so they add these special characters to either denote the function signature or add unique identifiers to class names that might be the same across namespaces. But basically, we just have to remove the question mark, the AV, and the 2 @ after it to get the full class names. Now, since each class has only one set of functions that it can call, all the smokers and all the boomers and all the other zombie types will always point to their respective type info. So what we can do is we can build use a map structure here to build a cache. So we only have to calculate this type info once, and then we can just use the vtable pointer here to detect the class that it's actually referring to. That will make sense a bit more when we start writing in a second. So the first structure, so let's start by writing in the memory handler. We're going to write a function that will take a vtable pointer and then return the respective class name. So the first structure we were talking about was the RTTI complete object locator. So that's RTTI or runtime type info complete object locator. First member is going to be the signature, which usually just tells you that the 2 next members, the p-type descriptor and the p-class descriptor, are going to be image-based relative offsets, which are just the pointers you're used to. So something like client base plus 0x5 or something like that, instead of just being direct pointers. 99% of the time, this is going to be a constant, which is just going to be using those image-based offsets. Following from that, the next member is just going to be the offset itself. The offset, depending on the signature, will be, like I said before, relative or absolute. Most of the time, the offset, 99% of the time, is going to be 0. So we don't usually have to worry about this. You would only mess around with this offset if you wanted to read what the class inherits from. The next one is going to be the CD offset. Now, I'm not too sure what this one does, to be honest. It's for some optimizations regarding virtual inheritance. Most of the time, you don't need to mess around with this. The next one is going to be the one we're looking for, which is the pointer to the type descriptor. So that's going to be another UI32T. And the last one is going to be a pointer to the class hierarchy of that vtable. So basically what classes this inherits from. Now there's a couple more members that we could add here, but we're not really going to use them, so we'll just go on with the other type, which is the one we're actually using now, which is the type descriptor structure itself. Let's call that type descriptor local. The first member is going to be a pointer to the B table of this type info. Again, we don't mess with this at all. The next one is going to be that reserved variable that doesn't really get used anywhere. It's just a placeholder in case it gets used in the future. Let's call it spare or reserved, or what you want to call it. And then the last one is the one we actually need, which is that character or that class name. And let's make that a size of 128 just in case. Usually it doesn't go over that much, but it's not going to cost us anything. Now, since there's only one type info descriptor for every vtable, so there's only one type descriptor for every class, we can build a map to avoid having to read this type descriptor every time we want to get a class name. So make a new variable here. Let's make an unordered map. I can spell it. It's going to obviously take the address of that vtable or that object pointer and an std string for the actual class name. And of course, let's include that. There we go. First, let's write the function to actually demangle that name. By demangling, I just mean, let me go back here, removing all those weird characters from it. So let's make a new function. It's going to return an std string. Let's call it demangle Microsoft Visual Studio Compiler, and it's going to take a constant std string, reference to mangled. I guess you could also use string view as well instead. I'm not sure if you can do string manipulation on string views. This one's going to be pretty straightforward. We're just going to do if mangled.find, and we're going to find that question mark AV. It does find that, and mangle.size is bigger than 6. 6 because it's 3 on each side. And mangled substring, substring, mangled.size, maybe -2 is equal to at. It's a pretty standard function. If we do pass all of that, we just returned the mangled.substring of 4. That's the offset, and then mangled.size -4 or -6. Otherwise, we just return the original string because there's nothing to demangle. And this should be our find. So now let's write the function to actually build up our cache. So it's going to be a private function, or a public function, I mean. This is going to return the class name or an std string. Let's call this get class name for object. First thing we're going to have to do is read that vtable pointer. So we're going to have to read that address, and we're not going to add any offset to it because, of course, the first member to any class with virtual functions is going to be that vtable pointer. If it's not a valid v pointer, then we can't really do much, so I'm just going to return an empty string. Then we're going to check our cache, see if we have that vtable in our cache already, so we don't have to manually check. Then we're going to check if we actually already have that vtable in our cache, so we can avoid reading through all those structures to find the class name. We just do auto it is equal to class name cache.find, and we're going to find that vtable pointer because that's going to be our key. If we did find our vtable, or if we did find an entry there, so if it is not equal to class name cache dot end, then we can just return it dot second, which is going to be that string. Otherwise, we're going to have to manually read that type info and update our cache. The first thing we're going to have to do is subtract 4 from that vtable pointer and then read that so we can get the pointer to the RTTI class descriptor or object locator. So call pointer is equal to read memory of that vtable -4. Again, if we can't read that pointer, then it's invalid. So I'm going to do basically the same exact check, but with the call pointer. Then using that pointer, we're going to read the RTTI complete object locator, or the call. Once we read the call, we need to check that the p pointer to the p-type descriptor isn't invalid. So if call.p-type descriptor, if it's invalid, again, we just return an empty string. Otherwise, then we're just going to read that type descriptor. Then we're going to get the name of the class, so std string, and construct that from that character we have there, or that char array. Then we're going to demangle it, which actually we can just do std string demangled is equal to demangle from the mangled text. Then we're going to update our cache with our new ptable pointer and our string corresponding to that. So class name cache vtable pointer is equal to demangled. And then we just return demangled as well. Now, if we did everything correctly, we should be able to check this pretty easily. Let's go to our offset handler. Then in here, we can make a new string, std string class name. I'm going to set that equal to the memory handler, get class name from object, and the object itself is going to be this exact same address up here. And then we can just print out the class name. So let's run this, and I already had Left4Dead running, and we see a bunch of classes, which is great. They're demangled correctly. And because we are using a cache, it's not an expensive operation. It's only expensive when it's a new class. Everything else after that is a simple O1 lookup. Let me put a breakpoint so I can scroll through this. And so we have infected, we have survivor bots, we have tanks, we have jockeys, smokers, a bunch of other stuff. I do want to check if there's any subtypes like jockey hand or jockey, because I remember there being something like that that we have to watch out from when we're comparing strings. Doesn't seem to. Yeah, I saw it there. Smoker claw. Anyways, somewhere around here there was a smoker claw. So now instead we can use the class name instead of using the health or some other variable to determine the zombie type. And this should be definitely more consistent than what we were doing before. Now let's go to generated code, and there's a few things we're going to change here again. So instead of using HP like we were doing before, we can use the class name now, which should be significantly more consistent. There's also another thing that I completely missed out on. Now that we have a consistent way of getting the class name, we don't have to basically combine these two that have the exact same max health. Just put these two up into hunter and smoker. And I'm also missing the boomer, which someone mentioned. I don't know how I forgot about him. And let me check out everyone else though. Yeah, it should be all of them, hopefully. Let's go back to our generated code. We're gonna have to update this function, and I'm going to be a bit lazy here. Instead of using an entity wrapper like I did correctly for the items, I'm just gonna go ahead and take over 4 bytes of the class that we're not using to insert my own class member. Later on, I'm probably gonna have to move this around because the first couple member variables were for networking, and that's probably gonna be the next video. So, but for now, just for testing, let's make this a zombie type. Oops, zombie type. Since we're not using this specific spot right here, we just have to make sure we write to it before we access it. Otherwise, it's going to be garbage. And we also need a new function that's going to be a void set zombie type that takes a constant type name. We're setting the zombie type. We're setting the zombie type. We're basically just going to do a bunch of if statements. So if type name is equal to exactly spitter, then the zombie type is the spitter zombie type. And I'm going to do that for the rest. And if it's not anything else, I'm just going to return or set the zombie type to a non-zombie, which hopefully shouldn't happen ever. Now that we're actually using class names, we're getting the zombie type. We're just going to return the zombie type. And for getting the entity name, which we use for the ESP label, we can do a simple switch case statement using the zombie type. Now, of course, I could store the string in the class, but that's a bit iffy. So until I set the entity wrapper in the next video, or later on, I'm just going to return a simple string on every frame, which isn't too smart, but for now, it works. Now that we have that, we can go back to our offset handler and change our validation for entities. Instead of using all this HUD stuff, we can all this. We can just check that the class name or the zombie type is not, so entity server data dot zombie type is not equal to, or is equal to the known zombie, then we return. And of course, we're also going to have to set zombie type. Perfect. Now that we have this, now that we have a valid or a consistent way of differentiating between entities, now we need a way or a tool to actually make building those bone chains not as tedious. Because doing it by hand, I mean, we're still going to be doing it by hand, but hard coding everything is a pain. So we're going to build a tool for it. Let's start by writing those or setting those bone chains. So hopefully you guys get an idea what we're actually doing. So let me go to ESP.h. We're going to make a new structure, and let's call this structure entity bone index data. In here, we're basically going to have a vector chain or a bone chain for each body part. So a bone chain for the head, so head chain, for the torso, for the leg, left leg, right leg, and so on. I'm not going to include hands or toes here because I generally don't think they look good on ESPs or bone ESPs, but if you wanted to, go for it. Now that we have the index or the bone chain, we need another structure that's going to hold IMGUI's character buffers for those corresponding chains. So entity bone strings. This is what the user will type in to connect their bones. You could use this tool to connect the bones once and then hard code all of them, or you could just leave it as is and just let whoever uses the cheat, if it's you or someone else, also be able to modify their bone cache or their bone chains as they want. I think I prefer that one. And this is going to be the exact same thing. Instead, it's going to be char head 16. I think 16 characters for each one should be enough. And in these, we'll just be storing a simple bone chain like 1, 2, 3, 4, which will connect bone 1 to 2, then 2 to 3, and then 3 to 4, and so on. Okay, and here we're going to have entity bone index data, entity bone string for each individual zombie type. So let's make it down here, bone index data. And the first one's going to be infected, of course, bone index data. And then we can do that for all the zombie types. And we're going to do the same thing for the entity bone strings for each zombie type. Perfect. Now, because we don't want to be having to set these every single time we restart our cheat, we're going to have to add some saving or profiles. And for this, I am going to use RapidJSON. It's the same one I used in the last series, if you watched that, used regarding assault. It's going to be very similar. JSON.h. If you're using BC package, then you can just do BC package install RapidJSON. But just make sure if you're using x64, then you would do x64 Windows, and if you're doing x86, then you would put x86 here. Anyways, we need that, and we need the dockage. Okay, a couple of functions I'm going to write down real quick, just so I remember to make them. We're going to need update bone chain, which is going to take the std vector reference to the specific bone chain, the char pointer to the bone data, or the actual string that we're updating from, that we're parsing that 1 dash comma 2 comma 3 into a bone chain. And we need the bone data size. You might not need this, but just in case. And I need to update this as well. We're going to need void draw settings bones. it's going to take an entity bone index data reference to the specific bone data that we want to draw. Entity bone strings, and we're making a function for this because I don't want to hard code every single bone for every single entity. Instead, we're just going to draw it once and then just change what it's pointing to. And constant char pointer to name, which is going to be the name of the actual entity we're drawing. So if it's infected, there's going to be a little drop-down menu or a tree node for all the specific bones for that infected. And then we need something to update bone chain, we have draw setting bones, we need something to load the color settings. Because if we're already loading profiles, we might as well include all the settings. It's going to be very easy as well. That's going to take a constant rapid JSON value v, which is going to be basically a JSON subset, the key with our color, and the color we're actually writing to. Then we need save color setting, which is another value, the key, the color, and the allocator, which is just telling us where we're actually writing or where that file actually is. And then the last two are loading and the bones themselves. So load bone type and save bone type. Okay, so let's do bone chain first. This one should be pretty, I think. Actually, disregard that. We're going to have to parse basically a CSV or comma separated values and then update our bone chain according to that. Let's set int value is equal to 0. Now the way I'm going to write it is kind of a bit questionable because it's based on old code, which is on C. There's probably a better way to do this, but this is the only way I've ever done it. So let's go with this. Char C is equal to 0. Then we're going to iterate through the bone data size or all the entries. Since there's not that many, I'm going to make it a UI int 8, which goes up to 255. I don't think any entity has more than 255 bones. And if it does, I don't want to draw all of them. Size less than bone data size and I++. The character we're looking at is going to be bone data I. It's either going to be a value, like 1, 2, or 3, or a comma, or a dash if you wanted to do a dash instead. Then we're going to check if that character is a value. So if it's not a value, it's a number. So if C is bigger than or equal to the ASCII value of 0, and C is less than or equal to the ASCII value of 9. So if that ASCII character is between 0 or 9, then it's obviously going to be a number. Then in number is equal to true. It should be in number, not is number. If we're in a number, then we're going to set the value equal to the value times 10 plus C minus 0. So for example, if the first value we read was a 5, and then the next value we read was a 0, then we're going to have to multiply this original value by 10. Otherwise, if our value is a comma, or a character is a comma, or it's the null character, and you could also use a dash here if you wanted to, or some other character as a separator, but I like using commas because it's usually the most known because of CSVs. And in a number. So if we are in a number and we found comma, we're going to bone chain that pushback that value. We're going to reset the value back to 0 and set in number equal to true. Now at the end of this massive for loop, we're going to do another if number check. So if in number, then bone chain that pushback value. This is due to the fact that when you write a CSV, 1, 2, 3, the last number isn't being followed by a comma. So we're basically just checking that if there is a last number, then we just push that value. Okay, then let's do draw settings bones. There's a couple ways you can do this part. This is just the visuals really, or how you want to draw the UI for each specific bone entry. I like to do a collapsing header. You could also use a tree, or you can have an individual window for each individual entity. But I'm going to go with the collapsing header. So if I'm UI collapse and header for that specific name, then we just return because it's not open. If it is open, we're going to set the base ID and go to the name. And you'll see why we use that base ID in a minute. Because right now we're going to have multiple entities that will have the exact same bone chains. So imagine there's the infected zombie. It's going to have an entry in MGUI for, let's say, bones in the head. But if MGUI sees that our label for each of those entries is head bones, then it's going to give us an error. So we're going to have to change the base ID depending on the infected or the zombie. It will make sense in a second. For this, I'm going to be using a lambda function. So let's call it draw part is equal to brackets reference. So it has the scope of this function as well. So this lambda function will have access to the base ID and the name and any class members as well. It's going to take constant char to the part name, the char pointer to the string buffer, size t, I think that's what MGUI likes for the buffer size, and an std vector of that chain we're actually updating. Now this vector chain doesn't necessarily have to be a size int. It should actually be unsigned int 8t as well. I'll change that later. It should save some space. There's no reason we should have a couple million bones. Max there should be like 4, like 255 or something like that. In this lambda function, we're going to set the input label equal to the std string of the part name. We're going to add the IMGUI format, which is this 2 $, plus the base ID, which is out here, which is why we need this little reference here, plus the part name. So basically what this is doing is this is making it so that the ID of the actual thing we're drawing is head, or could be head, reference to infected. So what this is doing is it's actually drawing, this is the label we see on the screen, but the actual label that MGUI is using is head, $, infected head. And this is the label on that specific input. If we were to use head for every single input on every single zombie type, MGUI would give us an error, a start error, or it would just not work outright. Depending if you, I'm going to have the input text for that specific thing we're drawing. So in this case, this would be the place where you put 1.3, 1.3 for the bone chain itself. Then I'm going to do MGUI same line. So we have that button or that apply button on the same line as the input text. We're going to do the same thing for the apply button. The label for that is going to be the actual apply text. We're going to add the IMGUI format for the ID and the actual ID, which is the base ID, which in this case would be infected, and head. Then we're going to draw that button. When we do press that button, we want to call update bone chain, which we just wrote. We're just going to take the chain, the buffer with the actual CSV files, and the size of that buffer, which is buffer size. And that's it. And here, it's pretty straightforward. Now we just do draw part for each individual zombie type or zombie part. So head, bone strings dot head, size of bone strings dot text, and so on, and the bone data head chain. Now again, this specific function is only drawing the collapsing header or that little subset for that specific zombie type. So this is drawing all the inputs for the bone chains for, let's say, the infected. And then we're going to call this function for the infected, for the spitters, for the boomers, for the witches, and so on. Load color settings, we've done this function before. If you watch the other series, it's pretty simple. Now, I don't remember exactly how we did it last time, but it probably is going to end up the same way. So v.hasMember, you always want to do this hasMember check is object check. So otherwise, whenever you change the format of your settings and you try to reload or save that same data, it's going to corrupt your save. So it's good practice to just always check that you have that member variable before you try reading from it. Otherwise, you won't have compatibility across versions. We're also going to check isArray because it should be an array since we have 3 colors in one variable. And we want to check the v.key.size is not equal to 4. Or is equal to 4. If it is 4, then we just return. Then we're going to set the constant auto reference to array is equal to v.key. And we're going to update the colors. So dereference color is equal to I'm color of array 0 dot get float, and do the rest for the other 3 colors. All right. Now let's do save color settings, which should be pretty simple as well. Again, we're going to do that check because we want this to be compatible across versions. If you do decide to change how you're saving things, or just it gets corrupted, but you still want to use the save, you don't want to be able to lose everything. So now we're going to do a rapid JSON value. Color array is going to be a rapid JSON K array type. And then we're just going to push color array that pushback color value.x with that allocator that we passed in, which is basically just the file location. And we're going to do that for the rest of the colors. And don't ask me why IMGUI uses X, Y, and Z to store colors and values. It's a bit weird. But anyways, then we're going to add that specific member. So add member, rapid JSON, string reference to that key, a color array, and the allocator. So basically we constructed a color array, we added our colors to it, and then when we add the member, we're basically just writing to the file itself. We have load bone type and save bone type, and I think that might be it. Now this one might be a bit long, but it's just copy and paste. If not, bones.object has member for that name. If it doesn't have that specific bone saved, then let's not load it, otherwise it's gonna crash. And we're also gonna check that that bone object is actually an object. If it's not, then we just return. Otherwise, we're going to set the constant auto t reference or reference to t equal to bones object. So let's start off with the head. Do a little comment here. So if t dot has, yeah, let's make this capital T, just so it's a bit easier to say. I'm making a single character variable name because it's a lot of typing. So if t has member head, and t head is an object, and it is a string, then we're going to set the constant char pointer to s equal to getting that string. Then we're going to clear the IMGUI input on that specific label. So let's say you have 1, 2, 3 on the head bone. It's going to clear that label before it updates it, just to make sure we don't get any corrupted bytes left over beforehand. Then we're going to copy that string into the label, and then we're going to update the bone chain with those strings and bone chains. So now we have the head bone. So now we need to do basically all of this for each individual bone. Now I could use another lambda function to do this, but I think this is fine to just copy and paste and just change a couple things. So let me just do that real quick. It's literally the exact same thing, except just changing the labels and the variables themselves. And then we just have save bone type, which is a lot easier since we can do a really easy lambda function for this, I think. Rapid JSON value, let's call it type object is equal to rapid JSON k object type. Let's do an auto add field. Again, it's going to be equal to this little reference thing, so it has the scope of this function. It's going to take the constant char pointer to the field name and the constant char buffer of what we're actually saving, which would be the comma separated values and not the actual bone chain. We can parse that after. It's a lot easier to save as a CSV. In here, we're going to set the key, which is equal to the field name with the allocator. I'm going to set the value, which is going to take the buffer and the allocator. And then we're actually going to write that subtype object. Add member, the key is the key, the value is the value, and the allocator we're using is the allocator, of course. And now we just need to do add field to every single one of those. So add field head, and it's going to save the string of the head. And I'm going to do that for the rest of those. Once we add all the fields, we can save that and then actually write this value, which holds all these fields, into the actual JSON file. Let's write the JSON value, key name, the allocator, and bones object, and actually add that member from the key name, the value, which is the type object, and the allocator again. Now in here, we just need two functions, or yeah, I think two functions, load settings and save settings. Load settings is going to take the constant rapid JSON value reference, where it's going to actually write that JSON to, and void save settings, which is going to take that same value, where it's going to write load before, and the allocator, which is going to write to. Here we're going to need two functions. We're going to need load settings. For load settings, we just need to pass a constant rapid JSON value reference, the actual value with all of our saved settings. And in save settings, we're going to pass a rapid JSON value. It's to V. Actually, let's name both of these V. And we're passing by reference here because I don't want to copy over that whole JSON document. So of course we pass by reference to avoid that. And of course we also have to pass the allocator. So it's rapid JSON document allocator type reference to alloc. And let's make this function constant because it's not changing anything. Load settings is pretty easy. Since we're already here, let's include all of the things that we could save. So any of these variables except these four that the user could control and save on this profile. So if b.hasMember and enabled, let's not do caps actually, then enabled is equal to v enabled getBool. And let me do that for the rest of the Boolean variables. We do that for the rest of the basic variables. And then for the load colors, we just need to do load color settings, pass in the value. Let's call the first one item load color, and the pointer to the actual color. So item load color. And let me do that for the rest of them. Then we're going to draw the bone types or load the bone types. So if not v.hasMember, let's call it bones. Make sure we keep these names consistent across saving and loading. Otherwise, we'll run into issues. And we also need to check that it's an object. Then we set a constant auto reference to bones, or capital B actually, equal to v bones. And now we can just call load bone type for each individual one. So we pass B, the name of that actual zombie type. So the first one would be infected, the infected bone index data, and the infected bone strings. And of course, we need to do that for all of the zombie types. All right, now let's do save settings, which is basically the same thing, but changing the operations a bit. So in here, we just basically do b add member. We don't have to do any checks really. Enabled, so the name of the variable, the actual value of the variable, and the allocator. So I'm just going to copy over all of this. Then for the colors, it's basically the same thing, just save color settings, the value, name of the color, so item glow color or something to that effect, the actual variable, and the allocator. Next time I should start setting up these profiles earlier on so I don't have to write so much every single time. Instead, every time I add a variable, I just add one thing. But anyways, now we do the bones. So now we just call it save bone type, which should take care of it for us. The bones object, the name of that specific entry or zombie type, so infected, the infected bone index data, the infected bone strings, and of course the allocator itself. And we do that for all the bones. Then we just add the number. Bones, bones object, and allocator. Now we just need to update our actual menu, which should be pretty simple since we already have all the functions for it. So, so draw settings. Let's make a new tab down menu. Tab here. Let's have another separator. And then let's do if MUI collapsing header, however you want to do yours. So collapsing header. Make that bones. We're gonna have a little indent here because otherwise everything will be on the same line. It gets a bit confusing. And now we just have to draw settings, bones for each individual entry. So infected bone index data, infected bone strings, and so on for each single entity. There we go. Now if we run this, we should have a nice little menu. It's not going to do anything since we haven't updated our drawing the ESP, but we should have a little, there we go, little indentation. And each of these should have a little entry for you to put your bone indices in. Of course, you would only have to do this once because we're saving the profiles. And it goes up to 8, so that means the head can have up to 8 bones, which seems reasonable. So char 16 seems fine. So now let's actually go to ESP and draw our bones. So it should be pretty easy. So we just do entity bone index data. We set the bone index data default to a null pointer. And then we do a little switch statement depending on the type of the zombie. So if it's infected, then we would set the bone data equal to the address of that infected bone index data. And we'll do a switch case for each individual one. Now I made the default be the infected bone or the infected bones. We can also make the default just be a null pointer and do a little check here if that doesn't seem to work too well. So if bone data equals null pointer, or actually not bone data, we just return, or not return, continue, because if we return, we cancel out the rest of the bones. We just want to continue to the next entity. Then we just draw the bone chain for the points, and then bone data dot head chain, and then do that for the rest of the chains in that specific entity. Perfect. Now we just need a simple profile menu in our cheat manager. I am going to go and use exactly or almost exactly the same code I used in my last series because it's pretty consistent. I don't know why I would change something that works. So in here, we're going to, and let's do a function to actually draw this profile settings, just so it's not all in one big function. And we're going to need an std string function that strips the profile name. There we go. Now if we run this, we should have a nice little menu. It's not going to do anything since we haven't updated our drawing the ESP, but we should have a little, there we go, little indentation. And each of these should have a little entry for you to put your bone indices in. Of course, you would only have to do this once because we're saving the profiles. And it goes up to 8, so that means the head can have up to 8 bones, which seems reasonable. So char 16 seems fine. So now let's actually go to ESP and draw our bones. So it should be pretty easy. So we just do entity bone index data. We set the bone index data default to a null pointer. And then we do a little switch statement depending on the type of the zombie. So if it's infected, then we would set the bone data equal to the address of that infected bone index data. And we'll do a switch case for each individual one. Now I made the default be the infected bone or the infected bones. We can also make the default just be a null pointer and do a little check here if that doesn't seem to work too well. So if bone data equals null pointer, or actually not bone data, we just return, or not return, continue, because if we return, we cancel out the rest of the bones. We just want to continue to the next entity. Then we just draw the bone chain for the points, and then bone data dot the chain, and then do that for the rest of the chains in that specific entity. Perfect. Now we just need a simple profile menu in our cheat manager. I am going to go and use exactly or almost exactly the same code I used in my last series because it's pretty consistent. I don't know why I would change something that works. So in here, we're going to, and let's do a function to actually draw this profile settings, just so it's not all in one big function. Then we're going to need an STD string function that strips the profile name. There we go. Now if we run this, we should have a nice little menu. It's not going to do anything since we haven't updated our drawing the ESP, but we should have a little, there we go, little indentation. And each of these should have a little entry for you to put your bone indices in. Of course, you would only have to do this once because we're saving the profiles. And it goes up to 8, so that means the head can have up to 8 bones, which seems reasonable. So char 16 seems fine. So now let's actually go to ESP and draw our bones. So it should be pretty easy. So we just do entity bone index data. We set the bone index data default to a null pointer. And then we do a little switch statement depending on the type of the zombie. So if it's infected, then we would set the bone data equal to the address of that infected bone index data. And we'll do a switch case for each individual one. Now I made the default be the infected bone or the infected bones. We can also make the default just be a null pointer and do a little check here if that doesn't seem to work too well. So if bone data equals null pointer, or actually not bone data, we just return, or not return, continue, because if we return, we cancel out the rest of the bones. We just want to continue to the next entity. Then we just draw the bone chain for the points, and then bone data dot the chain, and then do that for the rest of the chains in that specific entity. Perfect. Now we just need a simple profile menu in our cheat manager. So in here, we're going to have a couple functions. Let's pick it down here. Avoid load settings, avoid save settings, and actually these should take a file path. So constant std string file path, and let's make it a reference so we don't have to copy over that string. And let's do a function to actually draw this profile settings, just so it's not all in one big function. Then we're going to need an std string function that strips the profile name. And again, it's going to do a constant std string profile name, so we don't have to pass by reference. And then lastly, we need a function to get all of the save files in the current folder. So let's do an std vector of std strings, get save files. Now for this, I'm just going to default to the working directory of the program. So if you run your program in the desktop, then the save files will be in the desktop. But if you wanted to, you could change this get save files to use a custom user-defined place, but usually don't bother with it. There's one caveat to this. If you run this, if your cheat or your external runs in a place where you need admin privilege, so let's say you run this in program files, that's the working directory of your cheat, then you won't be able to save profiles without running your cheat as admin. In that case, if you're doing that, then I would change the get save files to use the user-defined one instead, the working directory, or use something like the app data folder, which everyone has access to write to without privileges. So let's do get save files first. Up here, we need a couple includes. We need file system for keeping the files on the system. We need all the rapid.json includes basically, since this is for the main bulk of it's going to be done. And so we need the rapid.json.h, string buffer.h, writer.h, and document.h. Go down here. And I'm not sure why that's giving me an error, but I'll ignore it for now. So this is going to first initialize a vector of files. So I'm string of file. This is where the path comes into play. So if you wanted to change it to something else other than the working directory, like the app data folder, you would change it here. Since I'm going to be using the working directory, I'm just going to put a dot. And then we're just going to iterate through all the files in the working directory or the path that you passed in, and then check if it ends with the .json or whatever extension you want to make it. It doesn't have to be a .json. You could change it to like your name or something. It doesn't matter, just as long as you keep it consistent. So the constant auto reference to entry, that's an entry in the std file system directory iterator for that specific path. In here, we're going to check if that entry is a regular file and the entry path extension is .json. And if it is, we're going to push back the entry.path.filename.string, which is a lot. And then we're just going to return all the files. And let's see what's going on. I need to include string up here. Okay, let's do strip profile name, which is just going to remove the extension from that. So if you're using .json, it would remove .json. If you're using your own custom extension, you would remove that instead. So let's do an std string name is equal to profile name if name dot rfind dot // Just going to remove anything related to, I don't know, something like path dot / path or something like that. Just remove all of those entries. If those have that, then we're just going to remove it. So name equals name dot substring 2. And then we're just going to remove the .json. So first we're going to check that the file name has more than 5 characters, because obviously the .json extension is already 5 characters. So there's nothing to remove if it's smaller than 5. Then if it is bigger than 5 and the last 5 characters are the .json, then we're just going to remove those last 5 characters and return that new demangled or striped profile name. We have profile settings. Let's do that. Save that for later. Let's do load settings. So in here, we're going to have to open that file. So std string ifstream, or not std string, ifstream ifs file path, and it's ifs because it's an input file. Then we do std string content. It's going to be an std istream buff iterator for that specific file. And the iterator, or the thing it's iterating, is a bunch of characters. And I did forget to include fstream, which is why we're getting a bunch of errors. Exclude fstream. Once we open the file for writing, we're going to update our rapid.json document. Or not for writing, for loading. I'm sorry. We're going to parse that document. So document.parse content.cstring. Then we're going to get the ESP settings. So ESP JSON equals document.find member ESP. If it finds that object and it's actually an object, or it finds that entry and it is an object, then we're going to load those settings from ESP. Now, technically, I should have aimbot settings, but I think you guys get the gist of that, so I'll probably do that off screen. But it's the exact same thing. Actually, a lot easier because the aimbot doesn't have colors. But it would be the same thing, but aimbot here instead. So let's do save settings now. So now we need to open and write the file for writing. So rapid JSON, document. We're going to set the object of that document. So set object. We're going to get an allocator. Same allocator we're passing to the ESP later. Then we're going to let the ESP write its values to the settings. So rapid JSON value ESP object, good JSON, okay, object type. So basically, it's the same thing we've been doing before. We save the settings and then we add the number. And now I just realized that I have 3 T's in my settings for some reason. Then I would do the mbot if I remembered to do that before. And then we would do rapid JSON string buffer sp. We would make a writer using that string buffer. Actually, this could have been an auto instead of me writing all of this. And then document dot accept writer. Basically setting the writer or the document to use that writer. And now we can write the file. So we do std.of stream for output file stream. Pass the file path. If we do open the file, because sometimes you don't have permissions. If you try writing without permissions, your program will probably just crash. Throw in runtime exception. So if is open, then we ofs dot sb dot get string. So we write the string from the string buffer that came from the document, and then we close the file. Now we just have the profile settings. Now there's a lot of ways you can do this. I'm just going to do a very basic one. We're going to start with the classic if not imgui begin tab item. I'm just going to call it profile. If it's not open, then we don't have to draw anything. Then we're going to have another static std string for the selector profile, which by default will just be an empty string. And then we're going to have another static std vector that will hold all of the profile. And of course, this is static because I don't want to redefine it every single time. I also don't want to have to reload static, or not the static, the save files in the current directory every single time we call profile settings. So static std vector of std strings is equal to get save files. Then we're going to have a text input, or not a text input, just a text that says load existing profiles. Then like before, we're going to have a list box holding all of the available profiles found in the working directory or the file you chose. And for this, we'll also need to use the imgui ID we used before. So if imgui begin list box, and we do that little pound sign profiles. And I'm not doing anything before this because I don't really need text here. We're just doing the label itself. The size of this is going to be an im vector 2. Size doesn't really matter too much, except we want float minimum here. And then the actual size for that is going to be 4 times the size of the imgui get text line height with spacing, of course. So basically, this is going to make it so we have at least, or we're always at least showing 4 NC lines. It just makes it a bit more visually appealing than otherwise. Then we're going to iterate through all the profiles. So strip their profile names, and after we strip the profile names, we're going to set a new boolean. Boolean is selected is equal to selected profile is equal to profile. If that thing we're selecting is actually being selected by imgui, so if imgui is selectable, display that cstring is selected. So it's going to highlight it for us. Then selected profile equals profile. If it is selected still, then imgui set item default focus. Otherwise, we end the list box, close that off. And now we basically just need 2 buttons, one for load profile, one for delete profile, another one for create new profile, and a little text input for the profile name. So let's do load profile. So if selected profile is not empty, and on GUI button load profile. Then we just load settings with that selected profile. Otherwise, we do the button for the delete profile, which is going to be the same exact thing. Okay, maybe it wasn't the exact same thing. So if we're deleting a profile and it's not empty, we do sudo remove on that file. We update the current working files and we clear the selector profile so it goes back to an empty string. Otherwise, we're going to need, or not otherwise, but we're also going to need a text for creating a new profile, an input text that says the profile name. For this, I'm also not going to have a label on it, or it should be input text, not input double. Then we're going to have a new button that's going to be called button. In here, we're going to get the new profile name. We're going to add .json to it, or whatever your file extension is. Actually, this could be a little defined for it. We could just do like file extension is equal to .json or something to that degree. Anyways, we add the .json to it, we call save settings, and then we update the current working directory with our new files. And we end the tab item. Now, I think that should be all, probably. I guess we'll say a couple of things here. We have bone data initialized. I wrote it down twice. There we go. We have our classes. Nothing's being drawn, which is great because I haven't set any bone indices yet. We go back to the start. Then we can just go to this tank. We spawn zombie. See, spawn affected. DSP. DSP still works. Bones are not being drawn. Let me go back. I think I saved those somewhere. The ones I had before, just for the infected at least. Alright, so it took a couple of tries because I forgot I commented out on the bone indices, but now it works. So put 0, 1, 2, 3, 4 here, connects correctly. I can put 5, 6, 7, next one, or 0, 5, 6, 7. We have the legs on both guys. And now we need to check if it actually saves. So new profile, restart it, and it should load with the exact same profile, hopefully. Load, and we got our bones back, which is great. So now all I have to do is fill all of these out, save the profile, tweak it a bit, which is honestly not that bad anymore because I don't have to restart every single time. But it's a bit confusing, like where do you put the head? So that, do that real quick. Let me finish out one of them. And it's removing it when I'm close because I forgot to remove the distance check. Now that we have proper validation. Move 4 here for the head or for the torso. Let me do 9, 10, 11, 13. Guessing 12 is in there. And the head, let's do 13. I don't know what the center of its head is. 13 through 32 maybe. And then for the rest, for the right arm, it should be start at 13 as well, just so we have a common place where all those bones connect. 13, 15, 16, and 17, 18. And I need to remove that check because it's really screwing me up. So 13 and then 23 to 28. Except there's no, there's no 26 or 27. We have some, yeah, it seems to work. I just need to remove that check and everything should work just fine. Remove the bone indices. Anyways, I'm gonna leave it at that because this is a pretty long video already. I'll probably just do these off screen because it's just manual drawing. Let me make sure I save this. And yeah, when you save new profile and you already selected one, it should overwrite. But anyways, I'm gonna leave it at that. For the next video, I'll definitely get into networking because I think that's the most fun out of everything. That's how you get most of the exploits. Not sure how deep into Left 4 Dead 2 I want to go, just because it is a closed source game. You could get into trouble for that. So I might have a couple videos separate to that with an open source game first, and then do a couple lightweight ones on Left 4 Dead. But anyways, see you on the next one. Peace.